So we're going to talk about the net change theorem, and it's really just the fundamental theorem applied to real life situations. So we've said the fundamental theorem of calculus is an antiderivative, a definite integral from a to b of some value, and you can find the antiderivative, plug in b, plug in a, subtract the two, and that's the value of the antiderivative. Equivalently, you could say, well, big F prime is what's in there instead of calling it f of x. That's really what it is. If that's the derivative, this is the antiderivative, so of the derivative, and you plug your b and a in. So what is that? That's a derivative. What's another way that we've talked about derivatives? Derivatives are rates, right? They're rates. Velocity is a rate of change of distance over time, or a rate of change of position over time. Same thing with other rates. They're people per second. Usually in time, right? Think back to related rates. Almost all of them were d something dt's, right? Some change in something over change in time. And so if we have a rate and we take the antiderivative of that rate, we should get back to the original thing. So if we were talking about a rate of liters per second and we take the antiderivative of it, we should get back to liters, the original function. So let's do an example that looks like just that. A chemical flows into a storage tank at a rate. Keyword there, rate. We're talking about a derivative. A rate of this crazy expression per minute, where 0 to 60 is t, and t is in time in minutes. So we're talking about an hour. Find the amount of chemical that flows into the tank during the first 20 minutes. That is talking about finding an antiderivative, a definite integral at that. So I'm going to go from 0 to 20 because it says that I'm going to do it for the first 20 minutes, from 0 minutes to 20, well, seconds for that matter too, 0 minutes to 20 minutes. I don't care about all 60, I only care about the first 20. And then this is the rate at which it happens. So at 180 plus 3t dt. This is my f prime, my rate. I should put it in t, dt. If I take the antiderivative of that derivative, they're going to go back to give me an f value, a liters value. Now let me show you how that works out. This guy right here, it says right here, it's a liters per minute. Liters per minute. This guy right here is a change in time, right? It's a delta t, so that's a minutes. What happens to those minutes? They cancel. You get back to liters. It tells you how many liters have been changed over that time frame. So that keyword rate tells you about it's a derivative, tells you that the function given is a derivative. And so if you take the antiderivative of that, you're going to get back to the original function, which gets rid of the per minute or per person, per whatever. Okay, it gives the net change. To go back and fill this blank in, it gives the net change on the interval from A to B, the change that occurred on that interval. Now, this is a point where people also get confused. This is different from average rate of change. That's a very different thing. Remember our mean value theorem, average value theorem, same deal? Well, that had to do with this 1 over b minus a from 0 to 20 of all that same stuff. That is a little bit different. So let's go back and actually calculate the answers for both of these things and talk about what they mean. For the purpose of this video and other ones, we're not going to do them by hand, so we're going to use your calculator and get an answer. I'm going to get an answer for both those things. You do it too. And we're going to come back and talk about both those answers. So you see here, I got 4,200, and in this one I got 210. What does this one mean? Well, notice we canceled these out. The units we get on this is liters. This tells us how many liters were changed over that time of the chemical. There were 400, it's positive, so it was added. There are positive 4,200 liters added into the storage tank in that time. Now, if it had a leak in it, that would be how much flows out. You'd have this rate that it's flowing out. Also, you could figure out how much flowed out at that time, and then add them together and get a combined total change in the tank at that time. So this is how many liters we changed by. This is the average rate. Notice, This guy right here is 1 divided by the information, the numbers are A and B. Those are times. That's over delta T. That's 1 over time. So I'm not going to write time. That's goofy. I'm going to write minutes because this problem's in minute. And then this one right here, again, is liters per minute, right? Because that was a rate, right? That was a rate. And then this one is also a time. So if I just write these down in units, this 1 over minutes cancels with that minutes. And when I get it all said and done, it's liters per minute. And that's per minute. Look at my terrible writing. Okay, liters per minute. 210 liters per minute on average is what's going in over the course of those 20 minutes. Now, if you went all 60 minutes, you might find a different average, and you definitely find a different amount of change, how much was added to the tank during that time. So there's a difference between this integral that has, this integral is within this, but that fraction in front changes what the integral tells you in the interpretation of the integral. So net change is just the fundamental theorem. It doesn't have that fraction out in front. With the fraction out in front, it gives you average rate of change, a different thing. So in this example, if we are talking from 1970 to 1980, the rate of potato consumption in a particular country was this function. Notice it's a capital C. Millions of bushels per year. Bushels per year. And it's a rate. Both of those things, they deliberately and explicitly said it's a rate, but when they say bushels per year, that tells you it's a rate implicitly. It's implied. It's a rate because that's a rate unit. T being years since 1970, so 0 means the year 1970. And how many bushels were consumed from the beginning of 72 to 73. So how do we set that up? Okay, if we want to know the net change in bushels over those years, we're going to do the integral of the rate from the first time to the second time. Now, that's 2 because these are years since 72, and that's 3 because years since 73. Now, I'm going to actually write the function out. 2.2 plus 1.1 to the t dt. And if you do that, I got about 3.4669. That's truncated, okay, meaning it was just cut off. If you want 3.470, you could also do that as well. That's rounded because the number after this 9 was really a 5, so you round up. But you have to put the 0 because you need all 3 decimal places for this to be correct. Now, I am going to talk about the units on this. Now, this one, remember it says it's bushels per year. So that part, that expression is bushels per year. Now, dt, delta t, is a time. How much time changed? Well, 1 year, okay? Delta t, years. These cancel. So this gives us bushels. Actually, millions of bushels to be correct. Millions of bushels. Okay, millions of bushels. It's about 3.5 million bushels in that year were consumed. Now, again, if you put that fraction out in front, which doesn't make a whole lot of sense, it's 1 year time. You're going to the average rate of change over that year, but since you're multiplying by a 1, you end up getting the same answer this time. And again, this is one that you were definitely going to use our calculator for. It would be expected that on the AP test, and then these numbers you would be expected to store and probably use for later use. But either way, this gives us the same answer because of this value being 1, but here we have a 1 over years times bushels per year times years. Notice that cancels back out to a rate again, bushels per year. Okay, and so the last problem on this video has to do with a pump connecting to a generator, and it's operating at a varying rate. Rate, there's the key word, we're dealing with a rate. This is a derivative. So if I take the antiderivative, we're going to get rid of the rate part, the per minute, per whatever, per minute in this case, see, per minute. So it operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. The rate in gallons per minute at which the pump operates is recorded at 5-minute intervals for 1 hour, as shown in the table. How many gallons were pumped in that hour? And you're going, well, I have to take an interval, but how do I take an interval? There's not a formula. Well, when there's not a formula, we estimate. This is a graph. It's a graph just in tabular form, table form, rather than in graphical form. So if we're talking about this first interval from 0 to 5, it changes this much, right? Those are the two F values. So we're now talking about doing RRAMs, right-hand rectangular approximation method, and LRAMs. You got to pick one. The AP likes to use these. Okay, they like to do this and make you estimate using trapezoidal rule, which we haven't talked about yet, RRAMs, MRAMs. They will tell you which one. Okay, so RRAMs is what we're going to use. We're going to use an RRAM and then an LRAM. So if I were doing an RRAM, I'm using the right hand of each side of these. So if you think about from 0 to 5, 10, 15, 20, 0 to 5, the right-hand side is 5. So in this first interval, oopsie, that's not what I meant to do. In this first interval with those between 0 and 5, the right-hand side of that is 60. That's how tall our rectangle is. If I drew that, it would be up 60. Okay, the next point would be down here. So we're going to draw a rectangle like that, sort of, kind of. I'm not going to draw each of these rectangles, but my first rectangle is 5 on the bottom and 60 high. It's 60 because that's the right-hand side. So 5 times 60. Plus the next one from 5 to 10. Okay, it's also 5 wide at the bottom. 5 to 10 is a distance of 5. And then the right-hand side of that is 65 tall. Okay, if I go up to 10, 65, that's the right-hand side of that interval. 10 is the right-hand side of the interval 0 to 5. Plus the next interval from 10 to 15, that's 64 high. Okay, I use this number. Notice we use 60, then 65, then 64. It's 5 along the bottom, and it's 64 high. Plus 5, guess the next one's going to be 58. I think that instead of a parenthesis, I wrote a 6. I got a little crazy there. Plus, the next one is going to be, you guessed it, 57 on this next interval. Okay? And so on and so forth. We're going to keep doing that. I'm going to do 5 times 55 plus 5 times 55 again. Plus the next one is, let's see, I did 57, 55, 55, 59. And yes, you could distribute out the 5 and just do 5 times the sum of these. 5 times 60 and another 60. Okay, and then 63 and another 63 for that last one. Okay, because that's the right-hand side of this very last interval. So then you add all those together and get your answer. So I got 3,595 when I added all that up. What does that mean? It means 3,595 gallons were used during that time. Now, if you want to do average rate of change, you'd multiply by 1/60 in front of that. Now, that is an estimate. It is not a perfect estimate. It isn't necessarily an over or under estimate, but to get a really good estimate, do an LRAM and then average the two. So I'm going to do that. I'm going to do my LRAM and then show you my work that I got and see if we agree. But averaging those two is the absolute best answer you can actually get. So you see here, I got 3,570 gallons. And I just want to remind you, and if you're looking at these and wondering, where the heck, I can't get the blue stuff to erase, so we're going to just use my highlighter. Let's see, we'll do highlight in red. That when we're doing an LRAM, you have to look at each interval. So say I'm looking at this interval. Now I'm using the left hand of that interval, which would be the 0. 0 is to the left of 5. And on this next interval from 5 to 10, that 60 is on the left, and then from the next interval from 10 to 15, 65 is. So that's why I start at 68, and on that very last interval from 55 to 63, I use this 63, but then that 63 is on the right-hand side, so it's not used at all. So there's only one 63. So you end up not using one of the values because you only use one from each interval, and if you use every one of those, there's one more tabular value than number of intervals, so that's not good. So you can figure out on average, if you average those, excuse me, not on average, that was a poor choice of words because we're not talking about average value, but you can average those two to get a little bit more accurate answer. And I'm sorry, my calculator didn't like me for a minute there. I'm dividing by 2, and you should get 3,582.5, and that is actually considered the best estimate. It's not the best. It's not the best answer. Of course, the exact answer would be better, but if we're doing estimation, that's considered the best estimate out there. You can also get that same answer using something called the trapezoidal rule, but this is a way around doing trapezoidal rule if you don't know that, which we don't yet. All right, so the next video will be talking about same stuff, net change, but specifically talking about net change with respect to velocity, since velocity is a rate of change, and how maybe it looks a little different, and how you can apply it some more to the things we already know.